Hello! We are going to be taking some notes on 1.5 parametric relations and inverses. So the first thing to define is what it means to be a parametric relation. So a parametric relation is some sort of relation that is described by using some third variable. Some relations are best described by using some third variable, and often that variable is t, which is known as the parameter. Now, when would this be something that we would use? My very silly example is often if let's say I looked at the amount of sunscreen that I wear during the summer. So I put a lot of sunscreen on in the summer, right? Obviously, I want to be safe. And I also eat a lot of custard in the summer. So if I am comparing these two variables, as my custard intake increases, so does my sunscreen wearing. But is it because I'm eating custard that I just decide, oh man, I need to lather on the sunscreen? No, 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 that doesn't make sense. It's all about the temperature, right? In the summer, it is more sunny, thus I have to wear sunscreen. In the summer, it's nicer outside, it's hot outside. I'm thinking, I want a delicious cone from Kopp's. So there's a third variable, T. In this case, T could literally stand for temperature. That's relating these two things. As the temperature increases, my sunscreen wearing increases. As the temperature increases, my custard eating increases. So we're going to do a real quick example, and I'm actually going to have you pause the video in a second, but consider the set of all ordered pairs x and y defined by the equation. X is equal to t minus 1, and y is equal to t squared plus 1. It says find the points determined by t equals -3 through +3. So we are going to do this by setting up a table, t, x, which is t minus 1, and y, which is t squared plus 1, and we want t to be -3, -2, -1, 0, 1, 2, and 3. So take a moment, pause your video right now, calculate these values, plugging in 3 for t in both of these and getting an x and a y. All right, hopefully you paused the video and calculated your values. Then the second thing we could do is graph these, but we are really just going to be graphing the x and the y coordinates. So -1, 2, 3, 4, +1, 2, 3, 4, -1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I know I need to go up to 11 on the y's. All right, so we can plot all these points. So -4, 1, 2, 3, 4, 11, and +2, 11. So I did that one and this one. -3, 6, 1, 2, 3, 4, 5, 6, and 1, 6. All right, -1, 2, and positive, oh, never mind, sorry, I don't need that one, and 0, 3, and -2, 3. I guess that 1 point is not quite there. If I sketch in, hey, look what I've got. Oh, that was really bad, but hopefully you kind of get it. It is a parabola. So then it says, find an algebraic relationship between x and y. Is y a function of x? To find an algebraic relationship between just x and y, we are doing something called eliminating the parameter, which really just means getting rid of t. So one way to do this is to solve for t. So x is equal to t minus 1, t is equal to x plus 1. Then I'm going to take that and plug it in for t in my other equation. Y is equal to x plus 1 squared plus 2. That's my new equation. I've eliminated the parameter. And look, that would be a parabola. It would be a parabola that opens up and has a vertex at the point -1, 2. Now, if you weren't able to see that from the equation, that's okay. But the last question is y a function of x? And the answer is yes. So that's a very small intro to parametric relations. Let's talk about inverse relations. So inverse relations swap x and y. That's the main thing that they do. They swap the x and the y values. And what does that mean? Well, let's say we have f of x is equal to x squared, a parabola, right? So we've got the point x, I'm going to make a quick table, x, f of x, so 0, 0, we've got the point 1, 1, we've got the point negative 1, 1, we've got the point 2, 4, 2, 4, and we'll go negative 2, 4 as well, right? A normal parabola, nothing interesting here. Well, an inverse function or inverse relation swaps the x and the y. So if we want to plot the inverse relation here, we are going to literally switch these values. So 0, 0, those don't switch. 1, 1, those don't switch. But then we switch it to 1, negative 1, 4, 2, and 4, negative 2. So if I plot these, we got 0, 0, 1, 1, 1, negative 1, 4, 2, and 4, negative 2. Here's what we got. Notice that thing is a relation, like connecting these two variables, but it is not a function. Not a function. And that's kind of important because realistically, we are only interested in an inverse if it is indeed a function. And so how can we decide on that? Well, we can do something called the horizontal line tests, which helps determine if a function has an inverse that is also a function. All right, so I just said that a horizontal line test helps us determine if a function has an inverse that is also a function. So if a function does not pass the horizontal line test, then an inverse function does not exist. And we can see this pretty clearly with the last example we just did, right? If I look at, here's my parabola, this is my original function, f of x is equal to x squared. Okay, a horizontal line test, I haven't told you what it is, but I think you're probably smart enough to guess. If I can draw a horizontal line through it and it hits it twice, this does not pass the horizontal line test. And we saw that the thing we created, this inverse relation, was also not a function, right? If I drew a vertical line through it, it hits it more than once. There, let's say we look at x cubed, which looks like this, f of x equals x cubed. Well, this guy does pass the horizontal line test, right? I can draw a bunch of horizontal lines through it. So this function does have an inverse that is a function. Now we keep saying function and inverse. I haven't really given you full notation. F of x is the original function. F to the negative first of x, although we would never say that, we really read this as the inverse function. I can literally say f inverse of x. That's how I would read this. And the last thing on this page is a statement about what it means to be one-to-one. So if a function is one-to-one, f inverse of x exists. Now let's put that into context. This is saying one-to-one. Every x value has only one y value. And the reverse is also true. Every y value has only one x value, and this is really proved through the horizontal line test. So a couple other things about inverses. How do we find them? How do we find inverse functions algebraically? Well, we know that inverses swap x and y. So to find an inverse function, you are going to switch your x and y variables. You are then going to solve for y, and then technically step 3 is then rename that new thing as f inverse of x. So we'll be doing this example in class if you want to pause it and write this down. We don't only have to find them algebraically, we can also find inverses graphically. So if we know that they are swapping x and y, to find a function graphically, you are going to reflect the function over the line y equals x. And just like I said with the last one, we will be looking at this example in class. So if you want to pause the video and sketch this in your notebook, you can. Otherwise, you'll have time in class. And then the last thing is to verify if two functions are inverses. So why are inverses important? Well, if f of x and g of x are inverses of each other, then the following will be true. Then the following will be true. F composed with g of x will be equal to just x, and g composed with f of x will be equal to just x. Really? Inverses undo one another. Inverses undo one another. It's one way to think about them. So we'll be looking at this example in class, and I will talk to you then. Have a great day.